So I would like to ask the next author, Mr. Koji Onishi, who will present his paper, Controlled Fracture of Brittle Solid Materials Based on Wave Dynamics. So, please.
Thank you. Good afternoon, ladies and gentlemen. We have three talks in this session regarding dynamic fracture, and mine is related to the controlled fracture of solids using electricity. And this work will be done with my students in Tokyo, together with the construction company Sumitomo Mitsui. Anyway, so there's no point. This? Okay. Okay, sorry. So here are the objectives of this talk. So it is very important to develop controllable fracture techniques to safer and more efficient operation in construction and destruction of complex structures made of solid materials. And the newly developed electrical method to destroy structures may be dynamically more controllable than conventional blasting methods. But the physical process and mechanisms of dynamic fracture in solid material generated by so-called impulsive electrical discharge cannot be clarified yet. So here, as the first step toward further understanding of fracture by impulsive electric discharge, we perform experimental and numerical investigations, and especially the effect of geometrical and loading conditions on dynamic fracture of given model structures is considered. So what are electric discharge impulses? So in recent years, instead of explosives, the use of safer electrical energy to crush materials has been proposed. So we employ the EDIC system developed by Hitachi company. And here is the schematic view of the system. So the electrical energy stored in the capacitor here is discharged in a self-reactive liquid here within several hundreds of microseconds through an electric switch, and high pressure is generalized due to the rapid evaporation of the liquid. So the system is very simple and very controllable. And here is a typical example of dynamic fracture using electricity. So we prepared here cylinder, concrete cylinder without reinforcing steel bars. So the diameter is 500 millimeters and the height is 500 millimeters. So this model is symmetric with respect to the blast source, so indicated in red. So here is a cartridge containing that self-reactive liquid. So the model is symmetric with respect to this cartridge, except for the stability section here. Okay? And we detonate or we discharge electric impulses here, and we watch what will happen to this species. And we observe with our high-speed camera system how the structure goes. And here is the results. So this is the experiment recorded by normal home video camera. So it's a bit. So this is dynamic fracture due to electricity. And what happened? So probably we can you repeat the video again? So here is the electricity lines, and here is the cartridge. So, okay, let's say the fracture has started at the center and propagated outward. Is it right? No. The reality is not so simple. So here are the photographs taken by our high-speed camera. So here is the top view of the cylindrical specimen, and here is the center, okay, plus containing the cartridge. And what happened is as follows. So here is the center. From the center, yes, there is a crack, outbound crack, extending from the center to the outer boundary. But at the same time, due to wave reflection, I believe crack or inbound crack is propagating from the outer boundary to the center. And these two cracks, for example, approaches against each other and eventually merges. And so, yeah, okay. Okay, so, and what we saw with our home video camera is the final results. But in reality, the fracture development is more complex than expected. So this is a typical example, and we further performed experiments. So, sorry. Now we prepare rectangular concrete blocks. The size is something like this, without reinforcing steel bars. And every block has one or more blast holes containing cartilage, having the self-reactive liquid. And the size is something like this. So everything is indicated in these proceedings. And that cartilage is covered by swimming material, that is sand, and connected to the control unit of the electric discharge impulse classical system. And altogether, 10 blocks or 10 specimens with different geometrical loading settings have been dynamically fractured by electric discharge impulses in the field. And for instance, the number and position of empty dummy holes are changed, and distinct differences in dynamic fracture pattern owing to wave interaction with the dummy holes are found. But here, due to time and space limitation, we show you only 2 examples out of 10. Okay, so here is a rectangular specimen. This is the top view. And they are prepared for the field experiments and modeled in numerical simulation. So this is the so-called number 9 specimen, and this is the 10. Okay? So red and blue and yellow holes correspond to blast. So the red are blast holes, and blue are dummy holes, and yellow are screw holes. And these screw holes are drilled for carriage of the specimen using a plane. So it has no, let's say, no experimental objectives. So we must have these screw holes. But what we would like to know is the effect of these dummy holes. Okay, here in the specimen 9, we have blast hole surrounded by dummy holes. That means only this blast hole has cartilage. Okay? And the dummy hole is very empty, just an empty hole. Okay? And here is the square. And at the center of the square, there is a blast hole. Okay? And each square has blast hole. And we have 2 blast holes in this specimen and 3 blast holes in this specimen. So the pattern is the same, but the number are different. And what kind of difference can we find? So here are the experimental results. So we see the dynamically fractured specimens, number 9 and number 10. After the experiments, and this grid is 50 millimeters. And in number 9, the plug indirectly connecting the 2 blast holes is unnecessary covered here. And we have unnecessary fracture. We just want to have plugs here, main plug here. But unfortunately, in number 9, it is not achieved. While, on the contrary, in number 10, we have rather flat, straight main plug connecting the 3 blast holes can be found. So we can say the only difference is the number of blast holes or empty holes, but we can control by increasing the number of empty dummy holes. We can control the fracture direction. And okay, so this is the final pattern. And again, we observed with our high-speed cameras what happens to the number 9 is as follows. So in the case number 9, cracks may develop inside this square. Okay? We can see already unnecessary cracks inside square. And later, after the development of unnecessary cracks inside the square, we have main crack. And this crack, main crack is widened due to gas pressurization. So this photograph shows that the cracks are developed by wave propagation, and later widened. The opening will be widened due to gas pressurization. And it's not clearly see, but now we can see main crack later developed. And on the contrary, number 10, okay, so these are rather smooth main crack. What do we see? We have again unnecessary cracks because these sections are very close to the free surface, so we have free surface effect. but here no free surface effect. And in this case, cracks inside this square at the edges, as well as the main crack connecting the black hole, develop at the same time. And yeah, so these are totally different compared with the previous case number 9. So in this case, cracks are really controlled by the dummy holes. Really useful in my opinion. And okay, so here are the results of our model experiments. So observations of the crack developed in the rectangular specimen by high-speed digital video camera showed that in number 9, cracks on the top surface develop first in the squares formed by the dummy holes, and then the main crack develops. While in the number 10, the main crack running through the 3 glass holes and the cracks in the 2 squares formed by the dummy holes near the free surface on the side appear almost at the same time. So, and also it's important to notice that the dynamic fracture network induced by EDI develops first on wave propagation displacement, and then gas pressurization while in crack opening displacement, and the stemming material is ejected due to gas. This is very similar to the conventional blasting by explosives. So new technique, but with similar effect. Okay? So what are the physical background behind the difference? So we conducted numerical simulation using our self-developed finite difference code, and the numerical detail can be found in the sources. So I will omit the details. Yes, so maybe this is important. So although different physical quantities may be chosen for simplicity, the stemming material covering the cartridge and filling every blast hole is assumed to have the same material properties as concrete. So just for simplicity. Of course, we can do everything, but now for simplicity, we assume that. And here is the pulse shape, sine squared curve with time. And more important one is here, no specific fracture criteria is incorporated at this moment, because first of all, we must know how waves generated by the new technique, application of electric discharge impulses, propagate and interact with giving homogeneity. Of course, we can include some fracture criteria, but not included in this moment. And here are numerical results. So here number 9 and number 10. So with 2 blast holes and 3 blast holes. And this blue means compression, and white and green means tension. So that means, in this case, number 9, we have compression between the blast holes until the later stage. While in number 10, due to the reflection from the dummy holes and free surface, yes, so green region develop faster than number 9. So that means tensile cracks can develop easier with the geometrical conditions of number 10. So this is the physical meaning of the numerical results. So we have free surface effect here and here, and dummy holes have effect on wave propagation. So we have tensile region due to dummy holes. Yes, and due to the increased number of blast holes, we have tensile. Okay, 2 minutes. Okay. I will finish in 1 minute, basically. So that is what I want to say here, so more important. So, like in this case, a fracture crater can be incorporated for post-failure analysis. And for example, observed dynamic fracture in a reinforced concrete beam by blasting by explosives at an overcharge level can be well reproduced by our numerical techniques. But we must be cautious about our knowledge on real 3-dimensional dynamic phenomena and fracture criteria for modeling non-overcharge blasting. So, like applying electrical impulses. And what we want to emphasize is that our fracture criteria derive mostly from 1 or at most 2-dimensional experiments. For example, 1-dimensional frictional experiments for post-failure behavior. And for instance, we have still no consensus regarding fracture criteria for crack, kinking, and branching even for 2-dimensional cases. So even for 2D, there's no consensus. So yeah, my supervisor, Professor Rice, famous paper. And so, therefore, we must be very careful in implementing any fracture criteria for dynamic fracture by moderate blasting, especially in experimental cases. So, 3D and moderate blasting is very difficult to simulate fracture. So, here are the conclusions. So, do we have time or not?
Yes, okay. Yes.
Okay, so there are 3 points. So, we have performed field experiments to dynamically fracture brittle specimens by EDI. and recorded the fracture development by high-speed camera. And our special attention has been paid to the effect of empty dummy holes. So, but just increase the number of dummy holes can affect our really controlled structure development. And the physical background can be explained using our numerical simulations. And for controlled structural fracture and demolition, the simulation technique may be used to design optimal operation on blast and dummy hole structure. So that's all. Thank you for your kind attention.